Hello. In this video we review structure of sinusoids and the parameter of sine and cosine function. A typical sinusoid would take one of two forms, a cosine function or a sine function. The input argument would be in this form, omega t plus phi, and you can see here that the sinusoid depends on the time. And here we have a scaling factor a. We call the scaling factor the amplitude. The units of the amplitude depend on the nature of the signal. So if the signal sinusoid here represent a voltage signal, then A would be in volt. If the sinusoid describe a current, this would be an amp, and so on and so forth. Omega is the angular frequency, and it has units rad per second. Phi is the phase shift, and it has units of rad or degree. Okay, which actually makes sense that the input argument have those units. Sinusoids are trigonometric functions, and the input argument should be a phase. So the units for the time are second. So if you'd like to have a phase, the units of omega should be rad per second, so that when you multiply rad per second times second, you get units of an angle or a phase. And same for phi, which is the phase shift, it has units of an angle. So in this plot here we have the two functions, sine t on the left and cosine t on the right. Both have the same frequency, they have the same magnitude or amplitude. So here the amplitude is 1, which makes sense because when we studied the sinusoids, we know a relationship between the sine and cosine function. We know that cosine theta is equal to sine theta plus 90 degrees. So both the sine and cosine at the same frequency would have the same shape of oscillation, but only with some shift of a 90 degree. So the sine here with no phase shift start at the origin with a magnitude of 0, whereas the cosine start at the origin with a magnitude of 1. Now if I have two sinusoids oscillating at the same frequency but shifted in time like that, this time shift corresponds to a phase shift. So here the two figures give us sinusoids that oscillate at the same frequency with the same amplitude, but since we have a time difference between the two signals, this time difference is actually corresponds to a phase shift. So now let's formally introduce those parameters, magnitude, frequency, and phase shift, and study the effect of those parameters on our sinusoid. So the amplitude of a sinusoid determines the distance from the average value of our sinusoid to its peak. So for the signal, this point here will give me the peak. So here we have a magnitude of 1. On the right figure, the average value is 0. So the distance from the average value to the peak give us the magnitude. So here we have a magnitude of 2. So basically the magnitude as the scale of our sinusoid. Then we have another parameter, which is period. Period is tightly related to the frequency. So by definition, the period, take a symbol t, is defined as the time it takes our sinusoid to complete one cycle. So the sinusoid repeat. So the time to make one cycle is defined as the period. The inverse of this period defines the frequency. The frequency by definition is the number of cycles per second, and the units of the frequency is hertz. So if you have 1 hertz, this corresponds to having 1 cycle per second. So here we have a couple of examples. So within a time frame, if I have 1 cycle, then I say, okay, the frequency is 1 hertz. In the second example, I have 2 cycles. So this is cycle number 1, and then cycle number 2. So we have 2 cycles per second, so the frequency here has 2 hertz frequency. This last example, we have 60 repetition or 60 cycles in 1 second, so we say that the frequency is equal to 60 Hertz. By definition, the frequency is the inverse of the period, so f in Hertz is 1/second. How many cycles per second? So a related definition as the angular frequency. So the frequency tells us how many cycles per second. The angular frequency, you can think of it as how many, or what is the speed of your angle, so the angular velocity of your sinusoid. It has units of rad per second, and it is defined as 2 pi times f. And we can replace f by 1/t, so omega is equal to 2 pi over t, and again it has units of rad per second. So what is the change to omega? How the change of omega affect the signal? Since omega is actually linearly proportional to f, it has the same effect. Increasing omega would increase the oscillation rate of our signal. So the higher the frequency, the higher the oscillations. The lower the frequency, the lower the speed of oscillations. Now for this parameter phi, which is the phase shift. The phase shift actually represents a time shift of our sinusoid. Okay, depending on the sign of phi, you determine whether your signal is gonna be shifted to the left or to the right. So in the example below here, I have a signal with a positive phase shift. So you can see with the positive phase shift, our sine is shifted to the left. So we say, okay, like this sinusoid here is leading the zero, so it starts before zero. On the other hand, if I have a negative phase shift, now you can see that your sine starting at a later time than zero, so we say that it is lagging the zero. Okay, so a sine should start from zero, but now we have some time shift. So the phase shift encodes the time shift information. So what is the actual time shift that is being corresponding to a phase shift of phi? We have a relationship between the actual time shift and the phase shift. The time shift is equal to phi over omega. We know that omega is equal to 2 pi over f, so t naught is equal to phi over 2 pi f. Replacing f by 1/t, we also have this expression. So these three are giving you how much time you're going to shift your sinusoid given a phase shift of phi. One last definition that we have with sinusoid is the instantaneous value of a sinusoid. So the instantaneous value is the value of the sinusoid function at a particular time instant. So for example here on this figure, at time equal to 0.5 millisecond, the instantaneous value is 20 volts. At time equal to 2 milliseconds, the instantaneous value is 35 millivolt. So the instantaneous value is the value of our sinusoid at a particular time. So how to obtain it? So if I ask you, give me the instantaneous value at time t naught, simply you plug time t naught into the expressions that you have for the sinusoid. So the expression is a cosine omega t plus phi. You'd like to get the instantaneous value at t naught, you plug t as t naught here and solve for this function. Okay, so let's wrap up with a couple of examples to reinforce those definitions. So in the right here we have the signal, and the signal should be modeled as a sine omega t plus phi. We would like to determine the parameters of the sinusoid: amplitude, angular frequency, and phase shift. So we can start with the frequency, but actually easier than the frequency is the period. So if you consider this point, the sinusoid will complete one cycle at this point. So the time it takes to complete one cycle is the period of the signal. So we can observe the period of the signal t to be 20 milliseconds. If I have t, I can obtain f. F is equal to 1 over t, and this is equal to 1 over 20 milliseconds, and this is equal to 50 hertz. Once I have f, which is the frequency, I can obtain omega, which is the angular frequency defined as 2 pi times f, and this gives us 100 pi rad per second. Okay, so now we have omega. Magnitude is also easy. Magnitude is the deviation of the sinusoid from its average value. So you can see that the sinusoid is symmetric around this origin here. So the distance from the average value to the maximum is our magnitude. So you can see here the magnitude A is equal to 10 volts. Okay. Now, what is left as this angle phi, the phase shift. If we reflect on the signal is actually a cosine function because you have the peak starting at 0. And we know that the cosine is equal to a sine plus 90 degrees. So phi by inspection should be 90 degrees. But if we don't know that, we can solve for phi. So the equation to solve for phi, we can obtain it from here. We have a relationship between the time shift, omega, and phi. So we can write down that phi equals to t naught times omega, where omega is the angular frequency, t naught as the time shift. Okay, so far so good. Now, so what is the time shift? If you look, if you have a sine function start from a 0 at origin. But here I have the 0, it is not aligned with origin, it's actually shifted in time. So what is this time shift? This is t naught. Okay, so you can see here that t naught is equal to 5 milliseconds. Okay, so we plug 5 milliseconds here. We multiply by the frequency omega, which is 100 pi. This gives us 0.5 pi, which is pi over 2, and pi over 2 is 90 degrees. Okay, so this is how we solve for our sinusoid parameters: magnitude, angular frequency, and phase shift. Okay, now let's move to the second example. In the second example, we have a sine wave with a frequency 100 hertz, phase shift of 0. We don't have the magnitude, and instead we have information coming from the instantaneous value. So we know that the instantaneous value is 100 volt when the time is 1.25 milliseconds. The question asks about the value of the voltage at 2.5 milliseconds. So the question asks, please give me the instantaneous value at 2.5 milliseconds. So let's start with the given. So we know that the voltage signal given to us, V of t, is sinusoid with a frequency 100 hertz. So the angular frequency would be 2 pi times f, and then times t, and we have a phase shift of 0. Okay, we don't know the magnitude, so we keep it as A. We now know that at time t equals to 1.25 milliseconds, V of t is equal to 100 volt. So if I plug this time into the sinusoid equation, I can solve for A because I have the time value. I can plug in it into the expression that we have for the voltage. So I have A sine 2 pi times 100 times t, which is now 1.25 milliseconds. Let me correct that. So the time here is 1.25 10 to the minus 3. Okay, so the only unknown here is A, so we can solve for A. A would be 100 divided by the value of the sinusoid. Okay, so we have A equals to 141.42 volt. So far so good. Finally, now we can obtain the value of the signal at t equal to 2.5 seconds. So at t equal to 2.5 milliseconds, we can solve for v of t as A. We now have a value for A, 141.42, sine 2 pi times 100 times t, and now t is equal to 2.5 10 to the minus 3. If you compute the input argument of the sinusoid, this would give you pi over 2, and sine pi over 2 is equal to 1. So the value of the voltage, the instantaneous value of the voltage at time t equal to 2.5 is equal to 141.42 volt. So in conclusion, in this video we reviewed the basic structure of a sinusoid function. It has three main parameters: amplitude, which controls the scale; angular frequency, which controls the speed of oscillation; and the phase shift, which determines the time shift across the time axis. We also learned about the instantaneous value, which is the value of our sinusoid function at a particular time instant. And this concludes our video. Thank you so much.